Hi guys, today I'm going to be solving the USACO 2016 December contest, Silver. Problem 3, Moocast. So Farmer John's N cows, up to 200, want to organize an emergency Moocast system for broadcasting important messages among themselves. And instead of mooing at each other over long distances, the cows decide to equip themselves with walkie-talkies, one for each cow. So each cow has a walkie-talkie. These walkie-talkies each have a limited transmission radius. A walkie-talkie of power P can only transmit to other cows up to a distance of P away. So note that cow A might be able to transmit to cow B even if cow B cannot transmit back, due to cow A's power being larger than that of cow B. Fortunately, cows can relay messages to one another along a path consisting of several hops, so it is not necessary for every cow to be able to transmit directly to every other cow. So due to the asymmetrical nature of the walkie-talkie transmission, which basically means that since not all walkie-talkies have the same range, broadcasts from some cows may be more effective than from other cows in their ability to reach a large number of recipients. And please help the cows determine the maximum number of cows that can be reached by the broadcast originating from a single cow. So the first integer contains n, the number of cows, and we see that there are 4 cows in the sample input. Then the next n lines each contain the xy coordinates of each cow from 1 through n, and then followed by p, the power that each of the walkie-talkies of each cow have. So we can see here that the first cow is located at x equals 1 and y equals 3, and the walkie-talkie is going to have a radius of 5, or a range of 5. And we can think of uh, each walkie-talkie's range as a circle, because it's going to be able to transmit to each cow that is within a circle with radius of that power. So this cow walkie-talkie radius power can be described as a circle with radius 5 and center 1, 3, because this cow is going to be situated at x equals 1 and y equals 3. And we can see this holds true for each of the other cows. The second cow is located at x equals 5, y equals 4, and has power 3, and so on. According to the sample output, the answer is 3. So a broadcast from cow 1 can reach a total of 3 cows, including cow 1 itself. Or herself, I guess. So, first of all, we want to check that this is true. So I'm going to pull up Desmos, and I'm going to be graphing a few circles and checking if this actually works. Let's see here. Zoom out a little bit. Okay. So the first cow, if you don't know the circle formula, the formula is x minus a number squared, and this number represents the x coordinate, plus y minus a number, and this question mark represents the y coordinate squared, equals the radius squared. And using this formula, we can graph a circle for each of these cows to represent the range of their walkie-talkies. So I'm going to be copying this over a couple of times. Since there are 4 cows, I'm going to do it 4 times. The first one, the x coordinate is 1, so we put a 1 here. And the the y coordinate is 3. And then the radius, or the range of the walkie-talkie is 5, so we put 5 squared. And you can see here, if we also plot 1, 3, see that the cow will be situated at x equals 1, y equals 3, and this blue circle is going to represent the extent or the boundaries of the walkie-talkie. Oops. Yeah. then second cow, the x coordinate is 5 and the y coordinate is 4. The radius is, or the power is 3. And the center is going to be 5 comma 4. And we can already see here that the power, the range of cow 1's walkie-talkie has the ability to transmit to the second cow at 5 4, even though this cow's range isn't enough to transmit back to cow 1. And this cow, x equals 7 and y equals 2, radius or power equals 1. And this one, the last cow, power also equals 1, this equals 1, and the x coordinate is 6. For this one, the cow is located at 7 2, and for this one, the cow is located at 6 1. So I'm going to collapse this a little bit, and what we can see here is that if we start the transmission with the first cow, so cow 1, this cow is able to transmit to cow 2, but not any of the other cows, since cow 2 is within its range. Now, since this Moocast system can transmit to other cows indirectly, then we also have to check which cows cow 2 can transmit to. It's kind of like a game of telephone where they're trying to transmit messages to each other. And there can be some cows in between that are like messenger cows. And we can see here that inside the range of cow 2, cow 3 fits, and cow 2 is able to relay the message to cow 3. However, cow 4 is not within any of these ranges. You can see that this, the location of the cow is outside of each of these ranges of the blue circle, the green circle, and the purple circle, which basically means that none of the cows are able to communicate to it. And thus the answer has to be 3, because the most amount of connected cows, or like cows that can send messages to each other, is 3. And so how can we solve this? Now, what we want to do is we want to use some kind of recursive function that once we know the starting cow that we're looking at, so for example cow 1, then it goes to all the cows it can transmit to, and then it recursively finds which cows those cows can transmit to, and so on until we find the total amount of cows that this one cow can send a message to. And we can do this with the standard DFS algorithm that checks which cows are within this range, and then checks which cows are in the following ranges, and so on until it finds which cows are can be transmitted to in total. And I'll be showing this in code, and it's going to make a lot more sense when I show how the recursion actually works. And so what we want to do is first of all, we want to check each of these cows. But the problem is, how do we figure out if one cow is in the range of another cow's walkie-talkie? Or if this cow's walkie-talkie range can somehow like transmit to this cow. And what we can do is we can apply the distance formula in math, which is the change in the x coordinates squared plus the change in the y coordinates squared equals the distance between them squared, which is basically just an application of the Pythagorean theorem, a squared plus b squared equals c squared. And then we can gain like some kind of array list that stores which cows are within the range of a certain cow's walkie-talkie. And right now it might be confusing, but I'm going to be explaining it as I go along in code. Okay, so first, of course, we have to import our classes. USACO Moocast. We need n, we need the x values, we need the y values. I'm going to be storing it in separate integer arrays and the power of each cow. Then we also need the maximum number of cows, and yeah, let's just set it as that for now. Now we're also going to need a buffered reader in that reads the input and a print writer that prints out the answer. And we're also going to need a string tokenizer to, oops, that's going to be used along with the buffered reader. And this is all I'm going to be making for now. Zoom in so it's a little bigger. I'm going to initialize in as an input stream reader for now because we want to test the input and output. So first we initialize. And in this initialization, we're going to be, first we need to get n, and then we need to fill the arrays of p, x, and y. N equals integer dot parseInt st dot next token, and x equals new int of length n equals same thing, and p equals the same thing. And then for each of the cows that are going to be that we're going to get info on in the next line, n lines, to get the value of x, we need to initialize the string tokenizer first. Then we need to get the value of x. X of I equals integer dot parseInt st dot next token, and we do the same for all the rest. So y of I equals, oops, same thing, and p of I equals the same thing. And remember to throw our IO exception, because when we're using buffered reader, we need to make sure that we're throwing this exception. And then what we're going to need is we're going to need a way of keeping track of which cows can transmit to which cows. And one way we can do this is using an array list, an array full of array lists. So what this enables us to do is at a specific index of the array, we're going to have an array list that contains the number of the cows it can transmit to. So how we create this is using a static array list integer array called a, and then we initialize it by saying a equals new array list n, and for each of these array lists, they're going to equal a new array list integer. And then what we want to do is we want to draw combinations. So we want to compare each cow with each other cow, and then each of the remaining cows with each of the other cows, and so on. So what we can do is first we choose the first cow, and then we choose the second cow, which is going to be all the other ones. J is less than n. And what this is going to do is it's going to build pairs of cows so we can compare their distances and see if they can transmit to each other. So we have to make sure that we're using double since the distance is going to be a double in most cases, or it's going to have a decimal in most cases. So in double equals, so first of all, the change in x value, right? The difference in the x value squared plus the difference in their y values squared. And then we're going to have to square root this entire thing. Now we can't use a caret symbol in Java, so we have to do math.pow. The distance and 2, and what this is basically doing is it's raising xi minus x of j to the second power. And the same for this one, math.pow, this number as well as 2. So it's squaring the number. And then we have to do math.square root, and we should have the distance. And then we check if the first cow, so if cow I, number I, can transmit to ij, and we can do this by checking the power of cow I. So if the power of cow I is greater than or equal to the distance, then this cow can transmit to j. So we add it to the array list, to its own array list. And then if cow, the j's cow, has a power greater than the distance, then it can also transmit to cow I. So we add it to the distance. And that should initialize it. Max equals 1 for now. But we want to check if this actually works, so let's try printing it out. I is less than n plus system.out.println a of I. And since it's an array list, that's all we have to do. So let's try it. Let's get in the input and see if it works. Let's see. Huh. Okay, anyway. So this can't be st.next token, it's in .readline. So the first cow can transmit to cow 1. Second cow can transmit to cow 2. So this cow can transmit to the cow at index 1, so it's this cow. And this cow can transmit to the cow at index 2, which is this one. So yeah, cow 1 can transmit to cow 2, and cow 2 can transmit to cow 3. So that's all correct. And then we're going to do the solve portion where we use a DFS algorithm to see which cows are connected. So for each of the cows, let's say that the cow, the ith cow, or cow at index I, that's going to be the starting cow that starts the message. And what we want to do is we also want to make sure that there aren't any loops. For example, let's say that cow 2 actually had a power of like 5, just like cow 1. Then these two would be able to transmit to each other back and forth, but we don't want the algorithm to do that infinitely. So what we want is an array. We want an array called visited that keeps track of basically the cows that we've already visited. So static boolean visited. And we have to initialize this every time, since each time we're going to be checking a new cow that starts the signal in the first place. And we also need an integer that keeps track of how many cows we've visited. So let's call that count. And we also have to make this static, since it's going to be accessed outside of this outside of the function. So count equals 1, since we're starting out with 1 cow. And we do dfsi, and then max equals math.max, max, and count. And then in the end, we just have to print out max. And now is the time for the algorithm, dfs int I. That's going to be the original cow. First of all, we have to make sure that we mark visited. So since we visited the current cow at index I, we have to do visited of I equals true. And then for each of the n cows that this cow can also visit, so for each cow that this cow can visit, and we remember that we stored this in the array full of array lists called A. So if we visited this cow already, then we have to do continue. If we have visited this cow, we have to continue. So we have to look at the other cows, since we don't want an infinite loop in this recursive function. And if we haven't visited it, then we're just going to be adding count, since we're going to be visiting one more cow, and then we just have to recursively recurse to this cow. And yeah, that should basically be it. It's not that complicated. We're just doing what we would do like in real life if we were actually messaging, if there was actually a cow that was messaging other cows with walkie-talkies. Okay. DFSI can go up to n. Index 4 out of bounds for length 4. If visited n. Oh, wait. Visited equals new boolean n, right? That's strange. Oh, wait, if visited at n, I'm not very smart. Visited at cow. So if we have visited the specific cow, then we have to make sure that we don't look at that cow, or we don't transmit the message back. So we can see that we get 3 correctly, so let's try submitting it. Moocast.in, and out equals new print writer moocast.out. And then we just have to close these, so in.close and out.close. We have to close the files. And one last thing, we have to make sure that we're doing out.println instead of system.out.println. And yeah, let's try submitting it. It's Moocast. Yeah. Don't know why it's discolored here. And yeah, all the test cases were passed. And I hope this video helped you understand this problem. Yeah, thanks for watching.